Okay, guys, we're still talking about power in AC. And, unlike in DC, where power was power and is measured in watts, power in AC, there's actually three different kinds of power. We're going to talk about them one at a time. This is a review. You would have had this last year, so hopefully this will make sense to you, okay? So the first type of power that I want to talk to you guys about is called true power, okay, guys? And I've pre-written all this out so you didn't have to watch me write it out for you, but, pause the video if you want to take these notes or take a picture or a screenshot or whatever you do, okay, guys? So first type of power I want to talk about is true power, okay, guys? And true power is any power in the circuit that's caused by the resistors in the circuit, okay, guys? If you have resistors in the circuit, you will have true power. And it is power that's considered to be in phase. We drew it on that other drawing there, right? Here's our power that's in phase. There's our resistor, okay, guys? And true power is the type of power in the circuit that is actually measured by your kilowatt hour meter. And so, if you've got a house and it's got a meter outside, your kilowatt hour meter measures true power and true power only, okay? It doesn't care about any of the other kinds of power. And the reason your kilowatt hour meter is measuring true power is because true power is the power in a circuit that's actually doing work. And when I say work, guys, what I mean is, heat, or actual horsepower. If you recall from level 1, the definition for work is you've got to actually be moving something or heating something up in order to do work. And so if I've got a resistor in the circuit, it's going to heat up. But if there's a motor and it's producing actual mechanical power, that is also true power. Okay, guys? The symbol for true power is P, and that's the same symbol that you guys used in level 1, and that's because there were only resistors in level 1. Okay, so all your power was true power, and so it used this symbol right here. The unit is the same one that you learned in level 1. It's the watt, right? And the formulas here are basically the same formulas that you use for calculating power in level 1. It's the voltage of the resistor times the current through the resistor, okay? So I said that it's caused by the resistance of the circuit, and so true power is the voltage dropping across any portion of the circuit that's a resistor times the current through that resistor will calculate the power. Now, there were two more formulas that you learned in level 1 for true power, or for power in general, and it was power is equal to I squared times R, okay, or power is equal to E squared over R. And so those formulas continue to exist. It's going to be the current through the resistor squared times the value of the resistor, or the voltage dropping across the resistor squared over, the value of the resistor in ohms. All right, guys? So that there is type 1. It is true power. Now, what about capacitors and inductors? Well, capacitors and inductors cause a different type of power. It's called reactive power. And so we've got capacitive reactance and inductive reactance, and they both, XL and XC, right, guys? They both cause reactive power. And it is power that is out of phase, all right? And so we drew a nice little inductor here, and it was all out of phase, and the power's out of phase, okay, guys? And the thing about reactive power, guys, is the kilowatt hour meter ignores it. And that's because the kilowatt hour meter is actually measuring average power for the circuit. And so if you've got a big inductor in there, and the kilowatt hour meter is basically going to read the average of that, and if it's out of phase like that, then the average is 0. And that's because, there's negative power and then positive power, and negative power and then positive power, and they cancel each other out, right? And the other thing about that is reactive power doesn't do any work. And what that means is, this circuit right here, which is the true power, is all true power. That resistor is going to heat up. There's going to be 1200 watts, and you're going to feel it, okay? That's going to be a baseboard heater. This one here is also 1200 watts. It's the voltage, dropping across the inductor times the current through the inductor, but it's 1200 VARs, okay? But that capacitor, or that inductor actually, will not heat up, okay? We'll just sit there, do nothing, okay? You can't do any work with it. And if I had another circuit here with a capacitor in it, it would be exactly the same thing, okay? I'm not going to draw the phasors, but let's say XC was 12 ohms, and it was 10 amps, and this is 120 volts. This would also be reactive power, and this thing would be sitting here drawing 10 amps all day long. No heat. No heat. Okay? And if, because sometimes a student will say to me, hey, I'm going to put a big inductor in my heating duct. It's going to be 100 amps. It's going to heat my whole house, and my kilowatt hour meter is not going to move at all. All right? And that would be great if it was possible, but unfortunately, it's not true power. It doesn't cause any heating. And if it does cause heating, well, it's going to get hot. It's made out of copper. Yeah. That's because the copper is a resistor. Okay? And if it's getting hot because it's made out of copper, it's true power, and you got to pay for it. All right, guys? So, does no work. All right, so the symbol for that guy is VARS, and it stands for volt amps reactive, and that's also the unit. So our formulas are going to use the same, the symbol and the unit are going to be the same. All right, guys? And here's the formulas. Now, students get all wound up about these formulas. Van Andel, how come so many formulas, right? Well, they're the same formulas as this one, okay? The power, the reactive power is the voltage dropping across, and it says X here, which means it's XL or XC, or it's straight up X, which is the difference between XL and XC, times the current through the inductor, capacitor, or combination of the two. So it's still the voltage times the current, okay? It's just the voltage across the capacitor times the current through the capacitor, or it's a voltage across the inductor times the current through the inductor. Same with this one, I squared R. Now it's IX squared over X, XC, XL, whatever it is. And E squared over R, okay? So now it's EX squared over, X, XL, whatever that is, okay? So these work for inductors and for capacitors, which is why it just says X and not XL and XC and all that stuff. All right, guys? So that is reactive power. Hopefully this looks familiar to you. The third type of power I want to talk to you guys about is the apparent power. And the apparent power, guys, is the sum of the other two powers in the circuit, basically, okay? Because you have two kinds of power, and then this is the sum of the two. You've got true power and reactive power. If you add those together with phasors, you will get the apparent power. The symbol is VA, volt amps, okay? And if you've ever wondered why transformers are always measured in VA and not in watts, that's because the manufacturer of the transformer doesn't know what kind of load you're going to put on it. Okay, all he cares about is you can't load it up with any more, volt amps than it's rated for. Okay, so he's not going to measure in watts because you could be connecting it to an inductive load. Okay, and he doesn't want that, or he doesn't want you to be confused about that. Units is volt amps, and here's the formulas. Same formulas again, okay? The VA is going to be the total circuit voltage times the total circuit current. All right, guys? And it's going to be the total current squared over, the impedance of the circuit, I squared R, I total squared Z, okay? And it's also going to be the total voltage squared over the impedance of the circuit. Now, just for fun here, what do those phasors look like? Well, I've drawn them here for you, okay? The true power phasor will always be drawn on the horizontal line because it's the one that's in phase, right? The reactive power is always going to be drawn on the vertical line, all right? And, some students say to me, well, does it go up or down? And what about if it's a capacitor? And what if it's an inductor? And do I have to worry about up, down, and the other thing? No, okay? I say no. Some teachers might say, yes, it matters. I say it doesn't matter. Who cares, right? All you need to know is that it's out of phase from the true power by 90 degrees. It always will be, okay? And it's always going to be on the vertical line. And whether you draw it up or down, not going to make any difference, okay? Because the VA is going to be, the phasor sum of the two. And you can see by this diagram that you can calculate the VA for any circuit. It's going to be P squared, plus VAR squared, square root, right? Because this is always going to make a right angle triangle. We've been working on power, and we're going to try figure out, true power, apparent power, reactive power, and a couple of circuits in a minute. But before we do that, we need to talk about power factor, okay? And so power factor is just a number that we use to, give you some idea of, you know, how a circuit's doing as far as like how close to in phase it is, okay? And so the power factor, it's the ratio of true power to apparent power in a circuit, and the formula for power factor, and there's more than one formula. We'll look at the other one in a minute. The power factor can always be calculated, you know, it's the power divided by the VA, okay, and that will always work. If I take a look at my power phasor diagram here, here's the power phasor diagram from a minute ago, okay? True power is always on the bottom, VAR is on the side here, and VA is always the sum of the two, or the hypotenuse, which means the true power in the circuit is always going to be less, or, you know, less than or equal to the VA. If there's no reactive power, they'd be equal, okay? And so you can always calculate the power factor of a circuit by taking the true power and dividing it by the apparent power. And what it's going to result in is a number that's between 0 and 1, right? You're never going to have a power factor that's more than 1, because your power is always going to be less than your VA. And so it's just a number that's going to represent the circuit's, you know, phase angle basically. And if you say, oh, the power factor is unity or 1, that means that the phase angle is 0, basically, okay? If P and VA were equal, then the power factor would come out as 1, also known as unity, and you would know that that circuit is, you know, in phase or has no reactive power in the circuit, basically. A power factor of 0.8, you know, let's say you had 800 watts of true power, 1,000 VA, okay, you would end up with 800 over 1,000, you'd get a power factor of 0.8, and you would know in that circuit that there was some reactive power. The closer the number is to 1, the less reactive power you have. The closer that number is to 0, the more reactive power you have, because your VA starts to get really long with respect to your true power. Okay, guys? And so electricians are always talking about the power factor of a, you know, a circuit, and that's what that is. It's the ratio of the true power to the apparent power in the circuit, and here it is. It's a number between 0 and 1. If you're doing your homework and you finding out that your power factor is something more than 1, well, you did something wrong. All right, guys? Now, it's possible to also display the power factor as a percentage. In other words, if you have a power factor of 0.8, you could also say that that power factor is 80%. You just multiply your little number times 100 and you'll get it in percent. And from me, guys, you'll see it displayed both ways, okay? Sometimes I'll say the power factor is 80%. Sometimes I'll say the power factor is 0.8. Those two are completely interchangeable. Now, there's another formula for power factor, guys, and that's this one right here. The power factor is equal to the cosine of the angle, okay? And that is also a legitimate way to calculate the power factor if that's how you want to do it. And the reason that works, guys, is because it's trig. If you think about it, this here, this power, is the adjacent side of the triangle, and it always will be their true power. And the VA here, guys, is always going to be the hypotenuse of the circuit. It just always will be. And if you look at the, you know, if you look at K, okay, which is the cosine of the angle is equal to the adjacent over the hypotenuse. And since the adjacent is always the true power and the hypotenuse is also always the VA, it is possible to say that the cosine of the angle is equal to the true power over the VA. Now, since the power factor is equal to P over VA, you know, so I've got the cosine of the angle is equal to P over VA, and the power factor is equal to P over VA. It is possible to say then that the power factor is just equal to the cosine of the angle. Okay, this is equal to this. So either one of these two formulas, okay, guys, will work for calculating power factor, and this is going to make more sense, you know, once we start trying some questions.